So today we are going to get into actually analyzing building energy use. So if any of you are more mathematically inclined, like I am, you're probably going to find a little more interest in this type of stuff. This is also the first lecture that I'm splitting into two different parts just because there's a lot to cover here. And because analyzing building energy use, that's a very critical part of energy auditing. Okay. I think I mentioned in the first class that you can actually draw some conclusions just by looking at a building's utility bills. Knowing nothing else about the building, there are some things that you can figure out. So this is often the first step of an energy audit. A lot of times this happens before you've even set foot into that building. The reason being, these analytics are very useful to gauge the energy savings opportunity without putting in a ton of time. The reason that's important is a lot of times you are doing this part of the audit before you get paid. You're trying to get the customer in the door, and there is some amount of work that you have to put forward before you can get them to commit. And so ultimately, this is part of the sales process. To go to the customer and say, hey, look at how much money you could be saving. You can't not hire me to figure out how to save your energy. But how do we define what's high and what's low in terms of energy use? Well, the first thing that makes a difference is what kind of building do we have? What kind of occupancy? As an example, an elementary school should be using a different amount of energy compared to a high school or an office building or maybe a lab type facility. Those buildings are all used in very different ways. And what about square footage? How big are the buildings you're looking at? 50,000 square foot elementary should be using more energy than a smaller building. You would expect a bigger building to use more energy. You can also have location. We mentioned in the very first homework doing a lighting upgrade in Florida versus Alaska and how that can impact the energy savings. Well, a building, the total energy use of that building is going to be different depending on where it is and how those HVAC systems operate. So the most basic term that we use is to define how much energy a building uses is the energy use index, which is abbreviated EUI. Just because I know I didn't throw enough acronyms at you in the previous lectures. So here's one more. Energy use index, also called energy use intensity, depending on who you're talking to and what their company decides to call it, but it's the same thing. Fortunately, it's the same acronym as well. The reason EUI is very useful is this allows us to compare buildings apples to apples, more or less. It's not an exact science, but it does give us at least one potential way to compare one building to another. So it's not perfect. Usually it's good enough, especially when you're at this stage of the audit and you're trying to do things quickly and not spend a bunch of time for a project that may not happen. The way it's calculated is it is the energy use of that building measured in kBTU, 1,000 BTUs, per square foot of building per year. So this factors in how much energy is being used and what is the size of the building. As an example, let's say we have two schools. We're going to look at their energy use. So the first building, let's say you look at their electricity bills and they are using 350,000 kilowatt hours per year and 20,000 therms of natural gas per year. And it's a 40,000 square foot building. And at this stage, all you know is that information and that it is an elementary school. So for the EUI calculation, we have to convert into equivalent units into kBTUs, which these are the multiplication factors to get our electricity and gas into kBTUs. So the total energy used here is about 3.2 million kBTUs per year. Divide that by the area of the building, 40,000 square feet, and we get an EUI of about 79.9 kBTU per square foot per year. So that's the first building. And let's say you had a second school building. Uses a bit more electricity, 420,000 kilowatt hours. Also uses a bit more gas, 32,000 therms, but it's also bigger, 70,000 square feet versus 40,000. So if we run through the same steps on the energy side, we can see it's using quite a bit more energy per year, but that is expected because it's a bigger building. And then if we look at the EUI by dividing by the building area, we get an EUI of 66.2. And so looking at these two buildings, yes, that second building does use more energy, but when you're looking at the actual EUI to scale for the size of the building, you could say building 2 looks like it's operating in a more efficient manner. A similar term to EUI is the cost index, calculated in a very similar way, except this is based on the utility costs per square foot. So the units of that would be cost per year per square foot. And so that would sum up your electric costs and your gas costs. And you might find that this building is spending, say, $1.25 a year per square foot. Now, this is harder to benchmark compared to EUI. What's a good cost index? What's a bad cost index? The reason it's difficult as compared to EUI is this is going to depend on your fuel types. Electric heat is more expensive. So for an equivalent BTU of output, electric heat costs about 3 times as much. So similar levels of energy, but a very large disparity in the energy cost. Another quirk with electric heat is a 100% efficient fuel source, which will actually lead to a lower EUI compared to gas, which will be about 80% efficient. So you can get more BTUs output with electric heat compared to the input. But because electricity is so much more expensive, even though you have a lower EUI, that's going to give you a higher cost index. So that can kind of, that can throw off your metrics a little bit. You also have variable utility rates. So I think I mentioned on day one in central Washington, it's about 2 to 3 cents a kilowatt hour. In Spokane, it's about 8 to 11 cents per kilowatt hour. So if you're looking at a building in Spokane versus, let's say, Wenatchee, the same EUI could lead to a very different cost index because the utility rates are so different. So I mention all these downsides to using cost index, but it still does have a use. It's still useful to look at the cost index when you are comparing similar buildings, especially if you have the same customer, same rates, and same fuel types. So if you have a school district that has 10 elementary schools and they all have gas heat and they all have air conditioning, this is still a useful metric that you could use for that customer. So calculating the EUI, that's not hard to do. Collect their utility bills, sum up their electric use, their gas use, do the simple calculation. But from there, how do we know what's good and what's bad? How do we know if an EUI is disproportionately high, or maybe it's really low? Maybe they're already good and efficient. So to make that determination, we need something to compare the calculated EUI to, which this is referred to as benchmarking. So what are you going to compare your building to in order to determine if it's doing a good job or a bad job? One of the most common sources is the Commercial Building Energy Consumption Survey, which you might remember from, I think it was the first lecture, where I had a pie chart for an office building that showed on average where all that energy use went. And that came from CBEX. And what CBEX gives you is the average use for all kinds of building types across the United States. It's a monstrous data set, hundreds of thousands of buildings. It's collected by the U.S. Energy Information Administration. They've updated it, I think, in 2003, and then again in 2012, and now I think they're collecting another set of data. The pros is the data set here is enormous, hundreds of thousands of buildings. So there's a lot of data to pull from to use there. But the downside is the data is national averages. So I mentioned how important climate is and where your building is actually located. Well, this data doesn't tell you what the average use is for a office building in Washington. It's just across the entire country. So there are some limits to how you can use this data. The second one is Energy Star for buildings, which you've probably heard of Energy Star in terms of appliances. You go buy a Energy Star washing machine or dishwasher or refrigerator. Well, they have a similar program called Energy Star for buildings. And the way this works is your building gets certified as an Energy Star building if they're in the top 25% of buildings in that region and of that type. So schools are competing with schools, but schools in Washington aren't competing with schools in Florida. So this does take into account the region. So that's one advantage. The pros here are you can look up the approximate average EUIs and an Energy Star EUI target for certain building types. And in the homework, you get to do this. I think you'll have to look up a school in the Pacific Northwest, and it will tell you this is where we think you need to be to get an Energy Star rating on your building. And it's really useful to have a target. So if I'm at 80 EUI today, but if my target is 40, how can I get there? The downside to this benchmark is this is a moving target. Since it's defined as the top 25%, that's going to change year to year. And it's a much smaller sample size compared to CBEX. So whereas CBEX is hundreds of thousands of buildings. If I were to look up school buildings in the Pacific Northwest, it may have maybe 8 to 10 buildings that I can use to compare to. So much smaller data set. The third thing you can lean on is just your professional experience. So I've been doing this a while. I've done tons of school projects. I have a pretty good idea of what a well-operating school building should be doing in Washington. I just know because I've been through the process so many times. The advantages here, this is based on real data, projects you've worked on. You know more about those buildings than any of these other benchmark resources. You know, if you're looking at this new school, you can think of previous projects that were similar and use that to compare to. The downside, again, less data to work with, especially if it's a type of building that you don't really have experience with, in which case you might have to lean on some of these other resources. And bottom line, you can't always benchmark. Some prominent examples: industrial and manufacturing. Every single one of those buildings is a magic unicorn that they are the only building like that in the world. So just because you have 2 manufacturing facilities that are 100,000 square feet, you can't really compare them because they're probably making different things. They have different process equipment. So there's no good way to benchmark those types of facilities. Hospitals are another tricky one because hospitals can have a high variability in the types of services that they offer. Inpatient, outpatient, maybe some of them have more lab type spaces, which are very energy intensive, and maybe the hospital across town doesn't have those lab spaces. So that's another tricky one to try to benchmark. And when you're talking to your clients, it's important to tell them where this data is coming from. So if you give them an EUI target and it came from Energy Star, tell them where that came from and maybe include any caveats or anything that they should be aware of with that data. But even if you can't benchmark these kind of facilities, you can still look at their total costs. If you have a big facility that's spending 500 grand a year, maybe you can identify some things that can shave some of that energy off of their bill. And in that case, if you are spending $500,000 a year, even 10%, that's a good amount of money, 50 grand a year. Even though 10% is maybe not, that's not a very big number. And maybe it's easy to find 10% savings. And maybe that's enough to get you in the door. To estimate the savings potential of a building, and again, remember, this is very high level, sometimes before you even walked in to that facility. But what you're going to do, you're going to take their actual EUI that you calculate and compare that to some theoretical top performing version of that building. So they use schools as a common example just because we see them all over the place. If that school is spending $65,000 a year and they have an EUI of 67, and let's say you go onto Energy Star's website and you look up that target EUI. So what would a top performing school be estimated to use to be an Energy Star rated building? And so you come up with this target of about 45. So you're at 67. Maybe we can get it down to 45. To put it into another phrase, what could you be saving if you could bring your building to that Energy Star standard? So to estimate those savings, you just need to look at the delta of the EUI. How much are you going to save? In this case, if you can go from 67 to 45, that is about a 33% savings potential. Well, if you think they can save 33% and you apply that to what they're spending today, 65,000, that comes out to about $21,000 a year. And maybe that is enough to pique their interest, get you in the door. And this kind of analysis really doesn't take a lot of work. Once you have those utility bills in hand and you know how large the building is, this calculation is very simple to do. At McKinstry, we have templates where we just need to plug in the data and it just spits out this potential savings on the back end. But the key component here, what's the benchmark? In this case, we used 45 as our target EUI, but that is what all the savings potential is predicated on, is that 45. So it's very important to know, where did that come from, and are you confident about that number? This is still a high level analysis, but this can be an extremely useful sales tool. I mean, especially we've seen schools where their EUI is in the hundreds, 125, 150. And then when we show them, hey, top performing schools, they're down in the 45 to 60 range, and you're more than double that. And then they start to see what you're trying to tell them, and they can see the benefit of hiring you as a consultant to help them get down to that Energy Star level. An important piece to this relates to weather. So the energy use of a building, highly correlated to the weather. So if you have colder weather, you can expect your heating bills, usually that would be your gas bills, to go up. And then in the summer, the hotter it gets, you should expect your electric bill to increase from air conditioning. And so if you were to look at this summer to last summer, well, what if one of those summers happened to be setting record highs? You would expect your electric bill to increase. And so with this correlation here, you would expect this to happen. And really, it's what you want to happen. You should see that strong correlation with cold weather, higher heating bills, hotter weather, higher electric bill. Because if it's not happening, if their utility use seems to be independent of the weather, that can tell you that things are really screwed up. If your electric bill is about the same every month of the year, that tells you they're probably not running things the way they should be, and they're probably wasting a lot of energy over that year. So that can tell you if they have inefficiencies or poor operation of equipment. And again, this is an easy thing to see, which I'll show you some graphs here in a moment that can illustrate this. So how do we measure the severity of the weather? And that's typically measured in what's called heating degree days and cooling degree days, HDD and CDD. If you have higher heating degree days, that is telling you it was colder weather. You needed more heat, which is indicated by higher heating degree days. Conversely, higher cooling degree days tells you you had warmer weather. You had to run your air conditioner a lot. Typically, this gets expressed on a monthly basis. So here's a sample 6 months. It's not a full year, but this kind of helps illustrate the changing of the season. So in March, we had, I'm not sure where or what year this was from, but in this example, in March, we had 563 heating degree days and no cooling degree days. So that would tell us we probably wouldn't be running our air conditioner at all in March. And then in April, we still have a significant amount of heating degree days, but it's not as bad. So that would tell you it's starting to get a little warmer. It's still cold, but it's not as cold as it was in March. We're still not running our AC. And then in May, that's where we start to see the switch. So now we have significantly less heating degree days, and now we're starting to see cooling degree days. And it's just going to continue from there until July and August, where you're probably not running your heat at all, but you're going to be running your air conditioning a lot more. And you would expect in August, you're running it a lot more than July, which is more than June and May. And so this gives you a way to look at the weather data in a very simple way and gauge how bad was it, last year versus the previous year versus this year. So that's what heating and cooling degree days are, but how do we calculate these numbers? And this is all based on what's called the building balance point. Anytime you have a building, there is a constant transfer of energy. So if we are in the summer months and it's really hot outside, that building will be taking heat from the outside. The outside will be heating up the indoor environment. Or in the winter, when it's really cold outside, we're going to be losing heat to the environment. And the main driver in the direction of heat transfer is our outside air temperature. Buildings operate generally in one of two modes. This is simplifying it a little bit but for the purposes of this discussion and how we calculate these, this is how it's thought of. So the two modes, mode one, we are in a mostly cooling mode for part of the year, where we're taking heat from the outside. The hot sun is out there trying to heat up our building, and so our air conditioners need to be on. Or we're in a mostly heating mode for the other part of the year, where we're constantly losing heat energy, meaning our heating systems have to turn on. Now, there is some wiggle room there. You can have a scenario where some of your systems are in heating and some are in cooling, but most of the time we're in one of these two modes, heating or cooling, which means at some point, the building's going to switch over from one mode to the other. At some outside air temperature, it's going to have this switching point where the cooling systems will need to turn off and the heating systems will need to turn on. And so that idea, that specific temperature, that's what we call the building balance point. This does vary from building to building. Very commonly, it's between 55 and 65 degrees. And the reason that it changes, and I'll have an example here in a moment, it's all based on internal loads, meaning anything inside your building that is generating heat. So whether that's people, computers, lights, or really any kind of equipment in your building will generate heat. How much internal heat gain you have is going to change this balance point. So if you have very high internal heat gain, so let's say you load up a room with tons of people and everyone's got a computer and all the lights are on, that's going to lower the break-even point. And conversely, if you have low internal loads, like an absolutely empty room and everything's off, that's going to increase the balance point. To help illustrate this idea a little better, so on the x-axis here, let's say this is our outside air temperature. So if we are below 60 degrees, we are going to be losing heat energy to the outside. And as we get colder, that heat loss is going to be more and more. So if it's really cold outside, say 22 degrees, we have very high heat loss, which is indicated by a negative value. We're losing heat. And then on the opposite end, if we're really hot outside, we're going to take on a bunch of heat. But then as it gets a little colder, it's going to be less and less. And so at some point, you have to cross this axis. And hypothetically speaking, wherever you cross this point, that's kind of the break-even point. And your HVAC systems are not really needed or are running very minimally. So yeah, well, I just explained all this. So colder temperatures, buildings losing heat, HVAC heating is on. And then on the opposite end, we're gaining heat, so the cooling systems need to be on. And then we cross, and that's our building balance point. To try and illustrate this idea of internal loads, if you had a building that you're maintaining at 70 degrees and it is completely empty, so no people, no computers, no lights, there's nothing in this building. If the building is maintained at 70 degrees inside, your balance point is going to be 70 degrees. So recall, this is all driven by a delta in temperature. So if it's warmer than 70 degrees outside, you're going to have heat transfer into the building. If it's cooler than 70, you're going to have heat transfer leaving the building. And really, this is entirely driven by that delta T. And virtually everything we do with energy is driven by that delta T. Now, if we had an opposite example where we had a building, we're still maintaining it at 70 degrees, but now we've loaded it up with people, computers, all the lights are on. We have all this stuff generating heat inside. Well, if it's 70 degrees outside, you're not going to see any heat transfer into the building, but you still have all this internal heat gain, meaning you still need to run your air conditioner just because of all this stuff inside. Well, what if it's 65 degrees? Well, now the heat transfer will start to leave the building, but you're still generating all this heat. Well, what if you dropped it down to 60? Now the building is losing heat at a faster rate, but is it fast enough? And so that's why this balance point gets depressed the more internal gains you have. So in this example, I'm saying the balance point is 55 because that's the point at which all of this heat gain in the space is balanced by the heat energy that's going to be lost to the outside. So even from 55 to 75 degrees outside air temperature, we are still running our air conditioner. But then once you drop below that 55 degree outside air temp, then it switches into that heating mode. And so at 55 degrees, that's when everything's in perfect balance. You're losing heat at the same rate that you're generating heat. So to calculate heating and cooling degree days, It's not very difficult, thankfully. The first thing you need to do is calculate the average daily temperature of the day. What is a little unusual is how they define the average daily temperature. So the way they define it is they take the daily high and the daily low and divide by 2. This is a little odd because it's not really a true average. If you had a day where for some reason it was at the maximum temperature for a lot of hours in that day, it doesn't weight that at all. All it does is look at, hey, how hot did it get? How cold did it get? Divide by 2. The fortunate thing for our sake is that does make the calculation very easy. So once you have your average daily temperature, then we need to calculate the heating or cooling degree days for that day. So if you run that calculation and you find that your average daily temperature is below the balance point, what that tells you is that we needed to run our heating systems that day because our average daily temperature was below that balance point. In which case, you take the balance point and subtract the average daily temperature. And cooling degree days for that day are equal to 0. So this is calculated on a daily basis. Or if you do the check and you find that your average daily temperature is above the balance point, that tells you we had a warmer day and we needed to run air conditioning systems. Then you take your average daily temperature and subtract your balance point. And your heating degree days will be 0. So you cannot have both heating degree days and cooling degree days in any single given day. It has to be one or the other. So what you do, you calculate heating and cooling degree days for each day of the month, and then you sum it up at the end. And that's how you can end up with months that have both heating and cooling degree days, where in the beginning of the month, you might be tabulating heating degree days. And then as the season starts to shift towards the end of the month, you'll start tabulating cooling degree days, or vice versa. To try to visualize that a little better, let's say your building balance point is 55. If your average daily temperature is above that, you calculate cooling degree days and heating degree days will be 0, or vice versa. If you're less than your balance point, you calculate heating degree days and your cooling degree days are equal to 0. Real quick example, balance point, let's assume it's 55. We'll talk a little more here in a moment about how you determine your balance point. Your daily high, 95 degrees. Your daily low is 72. So if you calculate your average daily temperature, 83.5 degrees Fahrenheit. So in this case, because our average temperature is above our balance point, that indicates a warmer day. So our heating degree days is 0. Cooling degree days will be the balance point, or excuse me, will be the average daily temperature minus the balance point. And so for that day, you get 28.5 cooling degree days. Now just do that 364 more times to get your monthly totals. And this balance point is very important to note when you're doing this calculation, because that is the entire basis of degree days. If you were to try to calculate degree days using instead a 65 degree balance point, then that is going to shift all of the values by a fair amount. And typically we notate that with putting it in a subscript. So HDD 55, CDD 55, or we put a dash to indicate that's the balance point we use to calculate these degree days. And ultimately, you need to tell your reader or your client or whoever what your assumed balance point was. So this sounds awful, right? Doing this 365 days out of a year, maybe even for multiple years. The good news is if you go to a website like weatherdatadepot.com, they calculate it for you. Let's run through a very quick example. So on this website, it wants to know the location. So let's say Spokane, Washington. And then it wants to know what balance point you want to use. And then you can do 2 different comparison years. So let's change our balance point to 55. We'll run report. It tells you what weather station it's pulling the data from. So GEG, that would be the Spokane airport. And then we can see, so here's the base year, 2019, heating degree days, cooling degree days, and then total would be a summation of the two. And the reason why they show 2 years, or they allow you to compare 2 years, is that it's very easy to see how bad was one year versus the other. So on the heating side, in 2019, they had about 4,300 heating degree days. In 2020, they had about 3,700. And so that tells you in 2019, we had a colder winter. So I would expect my gas bills to go up in 2019 compared to 2020. Or I guess 2020 would go down in comparison. On the cooling side, they are both right about 1,500 cooling degree days, which tells you they were almost identical in terms of the hot weather severity. But if I were to change this balance point to say 60 degrees, we can see that all of the numbers get adjusted. So now my heating degree days have increased because now my balance point is higher, which means I'm going to need to be in heating mode more of the time. And my cooling degree days decreased because I'm going to need less air conditioning. So it's a useful tool, and this goes all the way, you can go back to 2011, not too bad. And so if I collected multiple years of utility data from a customer, I can use this to very quickly pull weather data for that building or buildings. Well, that's great, but how do we determine what is the appropriate balance point? Generally, we have a pretty good idea for most commercial buildings. If you have no idea, 60 degrees is a very common assumption and is probably going to be a pretty safe assumption. It used to be that 65 was more of the standardized assumption, but that was back when we had a lot less internal heat gain. People weren't using computers quite as much. And so now it seems like 60 is more of a common assumption because buildings today have a lot more internal loads compared to buildings 50 years ago. If you want to get a little smarter about it though, rather than just doing an assumption, what you can do is perform a linear regression at various balance points, which I'll have some slides here in a moment that hopefully illustrate this a little better. But the general steps are you take the monthly energy use, you plot that against the monthly degree days at various balance points. And then after you've done that regression, you can look at the R squared metric, which I'm assuming in your labs, you've done some level of statistical analysis, but a higher R squared indicates a better fit of data. So if you try multiple balance points and you see that 62 degrees, that fits the data the best. Well, that's a pretty solid way of determining an appropriate balance point. Typically, we need to pair our electrical use with cooling degree days because we know that higher cooling degree days means higher electric use due to air conditioning. And then we typically pair our natural gas use with heating degree days because higher heating degree days means we need more heat, which means more gas use. We don't typically use gas in air conditioning, so it doesn't make sense to pair cooling degree days with gas. And we don't typically use electricity for heating. Well, we do, but it's not as common. But what if you run through those steps and the data is just a poor fit no matter what? At every balance point you try, it just does not want to fit. That doesn't necessarily mean your data is bad. There could be some other reasons, like what if you don't have air conditioning? We see this a lot with rural school districts where they don't have air conditioning because they just deal with it. Or maybe their school is completely out in the summer and, well, maybe they get a little warm in May and June, but it's not worth installing a whole air conditioning system. If there's no air conditioning, that means you're not going to see that increase in energy use for a higher cooling degree day. Or like I mentioned way earlier on today, that could tell you that they are not operating things well. Or maybe you have a situation where you have a variable occupancy. So for example, what about a hotel? The energy use of that hotel will be highly correlated to how often people are staying there. And so you may have certain seasons of the year where they have lots of guests and then other seasons where they don't have as many guests. Or maybe their energy use is more dependent on other factors that have nothing to do with weather. So as an example, if you have a factory, the energy use is probably going to be more related to how much they produce. Weather will play a role, but it's not going to be the dominant thing. It's going to be more correlated to how many parts and pieces did they make. This is the general profile of an electric usage on a building throughout the year. So the blue line is how much kilowatt hours they're using. And so you can see it's relatively constant in winter and spring. And then as we get into the summer months, you start to see that increase in electric use, which is due to the air conditioners. And then it drops down back to that more or less flat spot. And if you were to plot the cooling degree days on the same chart, well, you can see, hey, our air conditioner ran a lot more when we had more cooling degree days, as expected. But one important thing here is even if we have 0 cooling degree days, there's still a lot of base use that has nothing to do with air conditioning. So this would be all of the other stuff. So computers, lights, we're still running HVAC fans. So there's still some base use there. And then just that strong correlation. So this is what you would expect to see. If this building has air conditioning, I would expect to see a rise in electric use with a rise in cooling degree days. And so if we were to plot the monthly kilowatt hours against the cooling degree days, in this case, I used a balance point of 60 degrees. So I plot these on a chart, and this is what I get. Throw a little regression on there so that we can actually get an equation. And now that we have this equation right here, we can actually use this to predict how much electricity this building would use. So the intercept, 129,627, that'll be the base use. When there's 0 cooling degree days, we still have some amount of use in that building. And so if you look at the chart, that 129,000 correlates to right there, because that's your intercept. So regardless of cooling degree days, you're using that amount. And then we have this variable here, 156.29 times our variable, which is cooling degree days. And so now we can say for every 1 cooling degree day in a month, we expect them to use about 156 additional kilowatt hours that'll be added to the base use. And now we can predict how much electricity they're going to use depending on how severe the weather is. And then the R squared of 0.9379, that's a very, very strong correlation. And so you would look at this data set and say, I feel very confident in how this data fits. The air conditioning use is highly correlated to cooling degree days as expected. That's what we expect to see. And if we take a similar approach on the gas side, so if we plot the build use in therms, which is the blue line, against the heating degree days, we can see an extremely strong correlation. I mean, those are essentially running parallel to each other. And so as you have those higher heating degree days, you expect your gas use to go up. And you can see we still have some base use, similar to electricity. So even in those months where we have no heating degree days, we're still using some gas. But generally speaking, it's way, way lower compared to the electric use, because the only thing gas is typically used for in those summer months is to run a small water heater, maybe some kitchen burners too, or something like that. But it's not like electricity where there's a very large base use on the electric side just because of all those other non-air conditioning things that need to still run year round. Take a similar approach. You plot your gas use against your heating degree days using the same 60-degree balance point. You plot those against each other, and you can see that as we increase our heating degree days, we see an increase in fuel use. That makes sense. That's what's expected. And so looking at that equation again, we have the same components here. We have the intercept. So this would tell us that they're going to use about 61 therms each month, just as a baseline use for the water heater or gas burners or whatever. And then we're going to add about 1.5 therms for each heating degree day in that month. And compared to that electric use graph, you can see our base use is significantly lower compared to the electric use, which was, more like this. An example of poor correlation. So in this case, you can see that the electric use is kind of all over the place with regard to cooling degree days. And the odd thing is the electric use actually goes down with our increased cooling degree days. So as it gets warmer outside, our electric use goes down. We can still try to run a regression on this and come up with an equation. And we do that and we see we actually have a negative slope on this. We're seeing a decreased use, and our R squared is 0.48, which is not great. That's a pretty poor R squared, which means the data does not fit very well. So one reason why this might be the case, maybe there's no air conditioning. That wouldn't explain the decrease in use, but it would explain why there's no increase. Or maybe the building's closed in the summer when there's high cooling degree days. So maybe they have air conditioning, but the building's closed, meaning all the other uses for lighting and computers, all of that actually goes down. And maybe that's why there's a decrease. So by just running these simple analyses, you can arrive at some pretty good conclusions at the end of the day without knowing anything else. If I were to look at an electric use profile, I could probably guess whether they have air conditioning, whether they're closed in the summer, maybe identify some unusual operating parameters, like on this fuel. I've seen a gas use profile that was essentially flat. And that is not what you expect. And that's not what you should see if you're running things efficiently, unless you truly have a year-round gas load that is truly needed. But in that case that I'm thinking of, it was a convention center. And what had happened is their HVAC controls were so messed up that they were just burning gas year-round. Didn't matter how warm or hot it was essentially a flat line from January to December. And I can look at that and say, there's a lot of opportunity there. And sure enough, there was. So to close things out, give me one moment. I know we're not getting done very early today. This tends to be one of the longer ones. The homework associated with this material, this will be your first go around doing homework in Excel. And what I call spreadsheet etiquette is pretty important. And you might not realize it. I certainly didn't realize it until I got more into, we'll say, the real world. Excel is extremely powerful. When I was going to school at Gonzaga, we used Excel for very basic things, and I just assumed it was kind of a simple tool, but I didn't think that any professional companies would ever use Excel, and that was entirely wrong. It's extremely powerful, and you will very likely use Excel in the future. So let's do it right. So when you're doing things in Excel, really important to document everything. Reason being, someone else may need to review your work, and it makes their life a lot easier. So I'm talking about me in grading your assignments. Make my job easier. One important thing to consider is to identify what cells in your spreadsheet are what I call inputs or variables, which are hard entered values. And then what cells are calculated values, which cells are using formulas versus which ones are you just hard entering in yourself. It can be useful to include some notes. Where did your values come from? What equations are you using? And you don't always need to explicitly state your equations. Sometimes you can describe what you're doing in a narrative sense. So, hey, I interpolated between the high and low outside air limits. That's pretty easy to understand. If you tried to write the actual equation for that statement, I might not know what the heck you did. Always list your units. That goes for all the homeworks. Please bold or somehow indicate your actual answer. I think I talked about that already. This is a big one. I see this being an issue every year. If you're running through an Excel calculation and you're going to use a previously calculated value in a new formula, reference that previously calculated cell. So what I mean, I will try to illustrate this. Let's say I have a cell, so that would be a hard entered 25 horsepower, and I want to convert that to kilowatts. So I use a simple formula. And then if I have another formula down here, let's say, we'll add another variable here. Say operating hours. So I have a 25 horsepower motor running 2,600 hours a year, and I want to solve for kilowatt hours. What you should be doing is referencing this cell to do that calculation. What I don't want you to do is type 18.7 times that. Because then what happens is if you realize, whoops, I made a mistake. It's not a 25 horsepower motor, it's a 15 horsepower motor. Well, this cell gets updated, but this one does not. Whereas if you simply reference that cell, you're good to go. And now you can change these to any value you want. And it'll make your life a lot easier. So that's a big one. Referencing other cells that you've calculated, don't just hard enter in that value. Which I just illustrated. So what if you change the first value? Now all of your formulas are wrong. Versus if you set it up right the first time and you realize you made a mistake, you just change that first value and you're done. And it's this idea that spreadsheets should be flexible. The coloring scheme you're going to see, because I do give you a starting point in the Excel files, anything in yellow, that's a user input. That is a hard entered value. Light gray, that'll be a calculated cell using Excel functions. So whether you're using sum or anything. Orange means it's a direct reference to another cell. So that can sometimes be useful to just reference another cell in a different part of the spreadsheet. So back to my example here. Whoops. So my inputs here are yellow because these are hard entered values, and these two cells are calculated. So I'll make those gray. And now, if we're all using the same etiquette, I can look at this and know, okay, this is my input, and then these are my calculated cells. And I also know I shouldn't be touching these gray cells because they're calculated. Some useful tricks. If you've ever locked a cell using the $sign, if you did it the old-fashioned way, you would just manually put in those $signs. But pressing F4 is going to add the $signs for you, which will lock the reference. So if you copy a formula down, it won't change the references, if that makes sense. But if you're using a laptop, make sure your function key is not locked. I've run into this myself, and it took me an embarrassingly long time to figure out because my function key was locked, which meant F4 did not do what I wanted it to do. Some basic formulas. I learned the first year I taught this course, I grossly overestimated the Excel skill level of the course. So some of you may be looking at this thinking, this is pretty basic, but some of you, this may be a revelation. So sum, average, slope. So if you have a set of y values and x values, like if you're plotting degree days against kilowatt hours, that's a good one to use for slope. Same thing with intercept. So using those two functions, we can come up with our equation. And you can plug in different data sets and use these functions to have it be a dynamically updating calculation. If statement, that's a biggie. I might come back, talk a little more about that because we're running out of time, but that is the single most important function that I use in Excel. The way to read that, if the statement is true, perform A, and then if the statement is false, perform B. So you could say, if this cell is greater than 0, do something. And if it's not greater than 0, do this other thing. Sum if can be useful if you want to sum a range of cells based on some other criteria, which the way you read this is you look at the cell range, and then it'll look at that cell range for a certain criteria, say if it is equal to a certain value, and then it'll sum the values in a different range. That one's a little hard to explain without a visual component, but the if function, that's where it's at. 99% of Excel problems can be solved with that if statement, so learn how to use it. You can do nested if statements, which would be an if statement in another if statement. So a quick example of that if function. So we have these cells that all have a value in yellow. And then in column B, we have a check. Is that value greater than 15? No or yes. And then in the next column, is it greater than 5? And this is how the formula looks. So if A2 is greater than 15, say yes. But if it's not, say no. And then same thing with using a 5. And this 15 and 5 could be referencing another cell. You don't have to hard enter in those values. Oh, I did have a visual example here. So sum if, let's say you are keeping some financial records where you paid some employees based on a certain date and how much you paid them. And then we have this little calculator here that sums up the total payments. So the way that works is sum if, and then it looks at A2 through A15, and these dollar signs note that these references are locked. So look at A2 to A15. So those are the names. And then check E2. So look for that name here in this column. And then sum C2 to C15. So look for John in this column, and then sum anytime it says John in this column. And so if you get good with these formulas, you just need to write it one time and then copy it down and you're done. So that's all I got. This is one of the rare times where I use all of the lecture time. But if anybody's got questions, homework or otherwise, happy to stick around. Otherwise, have a good weekend. I'll see you Tuesday.
Thank you.
Thank you.
Thank you.
Thank you.
Thank you.